Mad or brilliant? For today's problem, we're looking at this scene from Pirates of the Caribbean, where Captain Jack Sparrow and Will Turner are traveling underwater underneath an overturned boat and using this as a way to breathe while also being able to travel undetected. Will Turner pretty iconically has the line, "This is either madness or brilliance." Let's figure out which one it is. It is quite clearly madness. Let's see what the physics has to say about that. So I've sketched this problem out in a simplistic way. You can see that there is the boat under the water filled with air with the two characters carrying it. Let's take a look at some analysis. So throughout this analysis, I am going to be approximating a lot of things. Based on the result, you'll notice that those approximations probably won't matter. That first approximation is going to be that I'm going to pretend that this boat is a rectangular prism rather than a curved boat shape, because obviously it'll make the analysis a lot simpler. So let's take a look at the system as a whole, where that system is the boat and the two people. Of course, one of the forces that will be acting on them is the weight force, and that will be the total of the weight of the people and of the boat. So summing those together gives us the total weight. And the other force will be a large buoyancy force, which is just the force that we all experience, that any object in fact experiences when it's submerged in a fluid that forces it upwards. That buoyancy force will be the total of the buoyancy forces on the people and the boat as well, to form that total force. Now, another approximation we'll make is that the weight force of the people will be equal in magnitude but opposite in direction to the buoyancy force, meaning that the people submerged in fluid would just neither sink nor float and stay exactly motionless. When we go swimming, sometimes we neither sink nor float and just stay motionless there, meaning our buoyancy force and our weight force has cancelled out, leaving us moving in no direction. Therefore, we can simplify those total forces into just the buoyancy and the weight force acting on the boat, because this will make it a lot easier for us. So let's calculate the buoyancy force. The buoyancy formula is just equal to rho times V times G. Rho is that little P symbol, which means the density of the fluid. V is the volume of the object, and G is the acceleration due to gravity. To be able to calculate the volume, I'm going to just give this some estimated dimensions. I'm going to say 4 meters by half a meter by another half a meter for the depth. The density of the water is approximately 1,000 kilograms per meter cubed. The volume of the box is 4 times a half, which is 1 meter cubed. And therefore, I can calculate the buoyancy force, which is just 1,000 times 1 times 10, which is 10,000 newtons. So therefore, the upwards force acting on this box is 10,000 newtons. And the weight of a boat is typically under 100 kilos, and so I've just said, as an overestimation, 100 kilos meaning 1,000 newtons. So you can pretty clearly see then that the net force that's acting on this system is 9,000 newtons upwards. So no matter what happens, this boat is going to accelerate upwards, so you can clearly see that this situation is impossible. So why don't we get a more intuitive understanding then, instead of just a formulaic approach, of why this doesn't work, by comparing it to this situation here, where we have two people and a boat filled with air sitting on top of the water rather than being submerged in the water. In this situation, you now have even less of the boat submerged in the water, and this means that the buoyancy force that's acting on the boat is less than the buoyancy force from the first situation. We also have no buoyancy forces acting on the people, or at least no water buoyancy forces acting on the people in the boat, and so the upwards force here is much less than the upwards force of the previous situation. This means then that the downwards force needed to force this boat to accelerate downwards would be less than the situation that we had previously, and yet you do know, obviously, that we see this all the time, and there is no way that those people could, without filling the boat with water, actually get that boat under the water. So clearly it is just an impossible situation. Now, it's all well and good that I gave you the maths and the formula behind the buoyancy force, but let's take a look at what it actually is and where it comes from. So you can see here I've got a very simplistic sketch of a container filled with a fluid. That fluid might be water. At the molecular level of that, there are molecules bouncing around and coming into contact with each other. When they are doing that, they are obviously going to have to exert a force on the ones next to them. One molecule exerts a force on another, and according to Newton's third law, therefore that molecule exerts an equal and opposite force back on that first molecule. Now, these are doing this in all directions. All molecules are exerting a force in all directions, and this is kind of what we know as pressure. And of course, if they are exerting a force in all directions, then all of those other molecules must also be exerting an equal force in all directions too. And the pressure along a single line of depth or altitude is going to be the same. But as I go downwards, you'll see that the direct downwards force is not only the pressure force, but also a weight force. So as I move further down in a fluid, all of those weight forces stack, and you'll notice that the pressure increases with depth. So to be able to calculate the pressure at any depth, I'll need to first calculate the weight that's acting on top of it, and therefore what the pressure ends up being. I know that the weight of any fluid is going to be the density of that fluid times by the volume times by gravity. Of course, density times volume gets us a mass, times by gravity gets us a weight. Now, if I know that this is a prism shape, that container I'm assuming is a prism, I know that I can get the volume from area times height, where that area is the cross-sectional area, as you kind of see when I model that as a rectangular prism like so. Now, to get the pressure, I know that pressure is a force per area, and in this case, that force is a weight. So I know that my pressure is just weight divided by area, and I know that my weight is just rho Vg, and I also know that V divided by A just gets us H. So I'm left with P equals rho GH, where the pressure is just equal to the density times gravity times the height or the depth below the surface. So if I look at those effects on the boat, well then I know that the pressure is just rho times G times H, and I'm just going to assume that the depth under the water is just about 2 meters. I've just made a guess with that. It actually doesn't matter what I choose for that. I could choose any number and the result will still be the same. Now, therefore, the pressure at that depth is just 1,000 times 10 times 2, the density times the gravity times the height, that is 20,000 pascals. So there is a 20,000 pascal pressure on the top of that boat. And if I go underneath that boat at a depth of 2.5 meters, well then I've got 1,000 times 10 times 2.5, which is 25,000 pascals, acting on the bottom of that boat. And I know that the force is just the pressure times the area. The area being 4 times 0.5 because it's just a rectangle. And hence, that top force acting downwards is 40,000 newtons. And that bottom force acting upwards is 50,000 newtons. And therefore my net force is 10,000 newton upwards, which was the buoyancy force that we found from the first animation. So you can see, therefore, that's where buoyancy force comes from. It is just from the difference in pressure in the fluid, and then therefore the forces that act based on that pressure.